Assalamu alaikum students, I am Asma and I am here with the 10th program of calculus of BSCS level. We are studying about functions and today we shall study limit and its approaches. But before going to today's program, let me give you a brief summary of what we have studied about functions till today. We studied operation on functions, classification of functions, graphs of functions, graphing function by scaling, transformation and reflection, and domain and range of a function. As I told you that today we shall study limit and we will learn the topics like introduction to limit, tangent and area problem, existence of a limit, and some precise mathematical and geometrical discussion of limit. Students, how and from where the concept of limit was introduced, why we need limit, and what were the problems which tend to introduction of the limit. There were basically two problems for which the limit was introduced. The very first problem is called tangent problem and the second problem is called area problem. Traditionally, tangent problem is called differential calculus as well and area problem is called integral calculus. You can see the definition of tangent problem on the screen. For tangent problem, given a function f and a point p x naught y naught on its graph as you can see in the figure. So if we have to find out an equation of the line which is tangent to the graph at p, which is this purple line. For this problem, the limit was introduced. And as I told you that the limit was introduced for the area problem as well. So for area problem, given a function f, and if we have to find out the area between the graph of f and an interval a to b on x-axis, as you can see in this figure, that if we have to find out area between a to b under this curve, then we will use limit. To understand limit, we shall discuss both of them in another way. You can see a figure on the screen. As you can see in this figure, that this black line is called secant line and this blue line would be called a tangent line. So if p or this curve moves from a point p to q, the secant line will rotate toward the limiting position and the line occupying this limiting position is called tangent line. Same is the case for area problem. Now from area problem, we shall understand the concept of limit. You can see a figure on the screen. In the first figure, if we divide the region under the curve in rectangles of equal width and then we add area, and if we go on the same process and we repeat this for more rectangles, then rectangles will tend to fill the gap under the curve and it will approach to the exact area as the limiting value. So if we have to find out limit between a to b, which is under the curve, so for this purpose we will be using limit in further examples. Now we shall define limit after having the concept of limit from tangent and area problem. For the first example, which you can see on the screen, as you can see a function f of x is equal to sin x divided by x, and you can see the curve or graph for this function over here. It's quite clear from this function that when x approaches to 0, f of x approaches to 1, even from the left hand side or from the right hand side, functions approaches to 1. For some values in radian mode, as I told you that when we will put different values of x, as for this function sin x divided by x, if we put x is equal to 1, we get the function value as 0.8414 and same is for the negative value. And if we goes on putting different values of x in this function, so our function value will approaches to 1. And it's clear that the value on 0.01 is 0.9999 and for all the above values which would tend to 0, our function value will remain the same or it will move to 1. Students, we will be using some notations for limit as well. You can see some notations of limit on the screen. If we have limit x tends to 0 plus f of x is equal to L1, this is called a right hand limit as well. If we have limit x tends to 0 minus f of x is equal to L2, or it is called a left hand limit as well, or simply limit x tends to 0 f of x is equal to L. So these are some standard notation which would be used for limit. Dear students, now we shall consider different examples to understand limit. You can see an example on the screen. If for a single function limit x tends to 2 minus f of x is equal to 1 and limit x tends to 2 plus f of x is equal to 3. For the graph of this function, you can see that if limit tends to 2 from negative side, so it is equal to 1 or it tends to 1. Here it's quite clear from this dot that the limit at x is equal to 2 or x tends to 2 from negative side, 1 is not included. And for the second function, if we have limit x tends to 2 from positive side, then the limit tends to 3. But from this dot, it's clear that the 3 is not included in the curve or the graph of this function. For the second case, if we have the function value at 2, that is equal to 1.5, which is clear from this line, and this dot means that 2 is included in the value of the function. To understand the concept of limit from right hand side and from left hand side, we can consider one more example which is on the screen. You can see a curve of a function, and if on this certain function we put limit x tends to 3 minus, then the function value tends to 2, which is clear from this lower part of the graph. And if we have limit x tends to 3 from positive side, f of x would give a value as 2, which is clear from the above part of this graph. So for any certain function, if we put limit of 3 from right hand side or from left hand side, the function value tends to 2. Dear students, now we will define both of the reason with the help of diagrams and example. For the oscillation, you can consider an example which is on the screen. If we have a function y is equal to f of x is equal to sine of pi divided by x, we consider the first example as sine x divided by x. If we consider the same case, so we know that if we put limit x tends to 0 from negative side in this function, so it would give you infinity. And if we put limit x tends to 0 from positive side f of x, then it will give you the same number which is infinity. For this example, f of x is equal to sine pi divided by x does not have a limit as x approaches to 0, either from left side or from right side, because the function value oscillates between -1 to 1 as we consider in our very first example, and it will definitely oscillate between -1 to 1 without approaching to a limiting value. For the second reason, which was unbounded increase or unbounded decrease, you can consider an example which is on the screen. As I told you that we will be using limit x tends to x naught minus f of x for left hand limit, and we will be using limit x tends to x naught plus f of x for right hand limit. So if we consider this graph which is tending to infinity, even limit approaches from right hand side or left hand side. So if we consider that limit x tends to x naught minus f of x is equal to infinity or plus infinity, or generally we can consider that limit x tends to x naught on this specific function tends to plus infinity, which shows that there is an unbounded increase in the function, because when x tends to x naught from left hand side or the right hand side, the function gets larger without bound and consequently approaches to no fixed finite value. So in this example, it's an unbounded increase and the limit does not exist here. For the second case, which is unbounded decrease, you can consider the figure and example which is on the screen. For unbounded decrease, if for a specific function we use limit x tends to x naught minus f of x, and it gives you a function value as minus infinity, and if we put limit x tends to x naught from positive side f of x, it gives you minus infinity as well. Or more generally, limit x tends to x naught f of x is equal to minus infinity. For this specific function, we can consider this graph, and it's quite clear from this graph that when limit tends to x naught or x tends to x naught, our function value tends to minus infinity in both the cases, when x tends to x naught from left hand side or x tends to x naught from right hand side. So for this unbounded decrease, when x tends to x naught from left side or from right side, function value gets smaller without any bound, and consequently it approaches to no fixed value. So for this case, the limit does not exist as well. Dear students, now we will consider some more examples where the limit does not exist. For the first example, you can see on the screen that when we have limit x tends to x naught minus f of x, it gives you minus infinity, and limit x tends to x naught plus f of x gives you plus infinity. In both of the cases, for a certain f of x, limit does not exist, but for the left hand limit, when x tends to x naught from negative, limit is infinity or minus infinity. And for the second case, when limit x tends to x naught from positive side, limit does not exist or it approaches to infinity. Limit can also be used to describe how a function will behave as the independent variable moves infinitely far from the origin along x-axis or along y-axis. If x is allowed to increase without bound, then we write x tends to plus infinity, and if x is allowed to decrease without bound, then we write x tends to minus infinity. To understand the concept of limit at infinity through some examples. If we have a specific function f of x and we have this graph for this function, so you can see that if limit x tends to plus infinity f of x, then our function value approaches to 4, which is clear from this curve that x tends to plus infinity, then the function value tends to 4. For the second limit, if we have limit x tends to minus infinity f of x, then our function value tends to minus 1, which is clear that if limit tends to minus infinity, then our function value approaches to minus 1. So it's clear that for the limit x tends to plus infinity and minus infinity, our function will lie between 4 to minus 1. To understand the concept of limit at infinity more clearly, we will consider one more example which you can see on the screen. For this example, when x tends to minus infinity f of x, our function increases without bound and consequently it approaches to no fixed value. So over here, limit for x tends to minus infinity f of x does not exist, or it tends to plus infinity, which is clear from the graph that x tends to minus infinity, then our function value tends to plus infinity. And for the second case, if we have limit x tends to plus infinity f of x, then our function will approach to minus 2, which is clear from the graph of the left hand side. Then when x tends to plus infinity, then our y or the function value tends to minus 2. Students, here we will consider one more example to understand the limit at infinity, which is on the screen. If we have a certain function f of x and we have this graph for this function which lies between minus 3 to 3. So for this function, if we put limit x tends to minus infinity f of x, our function approaches to minus infinity, which is clear from the left hand side that as x approaches to minus infinity, our function approaches to minus infinity as well. And for the second case, if we put limit x tends to plus infinity f of x, limit does not exist, because when x tends to plus infinity, our function oscillates between minus 3 to 3, but it does not tend to a finite or a definite value. So for limit x tends to plus infinity, our function does not give a definite value. So over here, limit does not exist. So students, that was all for today's program. In today's program, we studied the concept of limit by tangent and area problem. Then we saw some notations which are used for limit, and in the end, we studied limit at infinity. Let me give you a very brief summary of today's program. In today's program, we studied introduction to limit, tangent and area problem, existence of a limit, and some precise mathematical and geometrical discussion of limits. Dear students, next program will be about left hand limit and right hand limit. Till that time, Allah Hafiz.